Hello my dear friends, today we're gonna talk about servos and to see if we can make them smarter. But before we actually try to make anything smarter, we have to understand how it works. So this is very simple hobby level servo. It has a plastic case over here, has a gear, it has a back plate and has contacts over here, which are power to actually power up the servo, ground and the signal. So as you know, each servo fed by pulse width modulated signal, and the timing of that signal will drive essentially this shaft and change its position. Like this particular servo has a 180-degree travel, so the lowest signal gonna be 0 and the highest timing whichever depends on actually particular servo, which would mean 180 degrees. So this is very simple driven servo using pulse width modulated signal. But what is actually servo? So there are two ways of answering the question: theoretical and practical. I prefer practical approach, so let's take it apart. So servo usually consists of few like parts. One is electronic and another is mechanical. So let's take a look how it's all look inside. So usually servo again has this few screws which you can actually unscrew right there on the back, which are gonna be housing obviously electronic parts, because hence the cables coming down here quickly. Usually the screws are pretty long because they try to go all the way through the case and actually secure back plate and front plate. Okay, so let's open up this back side of business. So what do we see here? We see electronic components, we see motor, right? Also we have three wires coming in and they go right to the controller board. Okay, what do we see on the other side? Okay, on the other side we see a bunch of gears. So this bunch of gears allow a reduction of the rotation of this motor shaft in comparison to output motor shaft. Sorry, to output shaft, motor shaft, output shaft. But there is one very key component is actually not visible. Let's try to dig to it. I'm not sure if that's gonna be easy because it looks like it's a bit potted. No, it's gonna be easy. And you look down there, you will see the resistor. So this resistor is necessary to have positional feedback. So how do you know that you reached your desired position when you say, for example, rotate it to 90 degrees or change your timing of pulse width modulated signal, which will correspond to 90 degrees. Yeah, you need this potentiometer. So it coupled with the output shaft, it will directly indicate the value of the, well, it's not measuring the value of resistance, it's actually the voltage divider. It's gonna just measure the value of a voltage divided by this resistor, so hence the 3 wire. So yeah, so this gonna indicate the position, and obviously inside this microcontroller, which is over here, which is not really like, it doesn't have any indication. I'm sort of fed up with all this stuff that all those microcontrollers do not have any like indication on them. I'll try to kind of look closer, but I don't think it has. Only those 2 driver chips, they have some data on them. Even that it's rare. Sometimes it's just all black. Anyways, so on the other side we have some power components. I guess this is essentially for driving the circuit. Curious with that. It's like, this is like core, like this is for resonator or something. Like looks like a usually resonator, this oval part. Anyways, sorry for slight tangent. So the basic of the servo as we see it. Oh, I got all grease on myself. Obviously servo has to be well greased because it has to rotate freely and nicely, and because they have so many gears, the friction will increase in each particular gear, so proper lubrication is very paramount for this. Also notice this one, this stud over here is actually a limiting stud. If you pay attention to to this top plate or top cover. So these things will limit the rotation physically, right? So this servo has 180 or a little bit more than 180 degrees rotation. So also there is an output bearing over here, which is nice. This is not every servo may have bearing, could be just bronze bushings, like for example over here, but our output shaft has the bearing, and probably, I don't know if its input shaft has the bearing or not, but hard to tell. It's very important. So let's put this servo back together, because there is nothing else to see. I'll try to put it nicely, not to break any wire. Okay. So after we saw what's inside the servo, let's talk about a little bit of theory. Okay, let's grab a piece of paper. Sorry if it's super bright. And so let's just draw quickly diagram of a servo. So obviously there is a servo controller, which actually sort of brains of operation. Controller, whatever. So there is 3 signals over here. One is VCC, another is actually VCC is usually in the center, ground, and the signal. VCC in the center is actually a really good idea, because if you put it like this or like that, you won't be able to mess it up. So VCC is over in the center. So this pin, red one, is VCC on this connector, Futaba connector. So this is inside the servo. So then we have a motor. Let's draw a motor like this. This is our motor. This is the motor shaft. 2 wires coming to the motor, and we have also potentiometer, and those 2 are coupled. And potentiometer has 3 because it works as a voltage divider. So doesn't matter like what's the polarity, because servo can rotate the motor in one way or another, servo controller. And potentiometer would have probably VCC is on one. Here's the sorry, it's not obviously ground. So center top would be our position. I'm not sure what it's gonna third one. It's grounded, or this is just somehow engaged in the circuit. So motor. This controller can employ all sorts of different algorithms in order to actually figure out calculate the position of the motor, but probably it use PID. So PID is proportional integral and derivative algorithm, which is implemented in this controller in order to actually precisely control the motor. So knowing the position of the motor will essentially stop the motor when it reaches the necessary position. So this is very important, and obviously this algorithm is quite precise, but those value PID are discrete value, and they are probably programmed inside of this microcontroller. So this is essentially block diagram of a servo. Sorry for very crude drawing, but this is roughly what it is. This is our servo. It can be hobby servo, or it can be like professional servo or something like that, or industrial servo. This is roughly how it's going to look like, and this is pulse with pulse with modulated signal, right? It's gonna look like that. So this is coming to this pin over here. Oh, sorry, to this pin over here, not this. So changing the value of this signal would reposition the servo. Right, so we know our basics of the servo. Like, there are many articles and many YouTube videos about how servo works. I just tried to do an intro, and I also will share with you very nice article found on the internet in the description to this video, which actually explain servo in very nice details, and also provide some basic schematics how servo works. So why, like, it's already pretty smart device. It already does the business. It has controller, it has, you know, its position. What I am missing, why am I to want to make it a little bit more smarter? Well, what I'm missing is actually knowing the position of the motor of this particular shaft outside the box. So what I would like to know is the position of the motor outside the box. So all this is known inside the box. You just say, put it to 90 degrees, and it just did it 90 degrees. But in any given time, you do not know what's the position of the motor, right? So if you turn on your device, you don't know the position of the motor. This is the biggest issue to me, because I would like to know this position. So how do we do that? Well, there is a solution. So here is my solution to the problem. This is the servo, and this is the microcontroller. The microcontroller, which is quite familiar to you, and this is our little tiny and favorite little beast called Trinket M0. So here what I decided to do. Let's go back to our diagram. In our diagram, I mentioned that we have this potentiometer over here, and there is a voltage divider. So what I'm doing, I'm actually tapping the value, okay, I'll move this back, of voltage from over here. V angle, I call it. So this voltage would indicate the position of the servo. So what I'm doing, I'm using ADC on this microcontroller, 12-bit, in order to read this voltage. All right. So let's go a little bit more in details. As I mentioned before, okay, I'll move this for now. So this Trinket is actually a very nice microcontroller, and it's super tiny. It has analog inputs, which can be up to 12-bit. So I decided to utilize this microcontroller in order to drive and read the value of that voltage, and then publish it over I2C bus. So let's go back into details. So right over here, I tapped this wire into the potentiometer, central wire, and now this essentially this microcontroller gonna read the value of the ADC, process it, maybe do a couple reads in order to actually eliminate the issue with some random values and precision and things like that, and publish it to another microcontroller via I2C bus. So this microcontroller is essentially a controller. So in this particular little project, I will show you how to work with adafruit itsy bitsy Bluetooth module, but Bluetooth is not engaged here. It's just how to work with this guy. Essentially, I just drive this guy. Also, how to work with Trinket M0, and I think this is perfect project for this little device, because it's super tiny, and essentially it may fit even inside this container. So the idea is that you're gonna read this value from your servo, and you have to know the voltage levels. For example, from 0 to 3 volt, this is 0 is like well, it's not going to be 0, but let's say 0. It's is your 0 degree position, and like 3 volt is your 180 degree position. So you have to measure it. So this value are programmed inside this guy. Also, what's also programmed in this guy is the I2C address. So this guy has I2C address. So this essentially becomes a smart servo. You have a brain over here, and you have a servo. If this is put all together, your servo become much smarter because it can publish its position. You can command it to go into position, but you fire and forget essentially. You just say go to 90 degrees, and you don't, your main controller don't care anymore. And this guy would say, for example, I reached 90 degrees, good. And now you can say issue another command. But if this guy is still reaching 90 degrees for whatever reason, is doing it slowly, or you ask him to do it slowly, your main brain, you don't have to be responsible for all those technical details. So this way we make this servo much smarter and much more versatile. Also, there is, depending on the technology, topology, I use I2C, this is chainable, so you don't have to have each individual wires coming from your whole bunch of servers to your brain or micro, like main controller. So now you can chain those servers from one to another, and it will save you on wires, on it make product much neater, and also each individual servo would be addressable. So if you're building some kind of robotic things which are not require super quick feedback, this would be, I think, pretty good idea to implement. So this is all just a prototype. You see all this pretty rough wires, and but I want to show you how it all works. In order to actually understand how it works, I'll have to show you some console feedback. And also I allocated a little project for that in GitHub, so I can share it as well. You can load in your little trinket and make yourself a smart servo as well. There is not much really to talk how it's all wired. Essentially, the servo is connected to the same power line as both microcontrollers. So it's going to be just 5 volts, but this particular servo is capable of 7.2 volts, but it works with 5 as well, 5, 6, and 7. This particular microcontroller will be powered right now in my demo from USB, and this one from USB. They connected only with ground line, so this is just ground. They would have separate power essentially to emulate the situation when they are two separate microcontrollers, but they could be on one power line. No big deal. It doesn't matter. Also, they are I2C lines are connected. SCI, SCL and SDA connected appropriately to this trinket microcontroller, and the ground. Also servo connected to the power, and this servo is powered together with this guy, and this is completely sort of separate. So what we can do, we can power all this up and see how it works. Ta-da! It works. So this controller tells this I2C slave to connect, to rotate the servo for every 15 degrees, and then it loops back 50, 15, 15, 15, 15, and then it loops back. And at the same time, it also asks the slave to report the servo position. So half a second set the position, next half a second read the position, set the position, read the position. So it's just in order to verify whatever was set. And this servo is fairly quick, so it reaches position pretty quickly. If this servo would be slow, or I would ask too quickly, it would be value somewhere in between desired position, because it takes time to reach that desired. For example, if we would say go from 0 to 120, and 100 milliseconds later you would ask about position, you would have some random value in between, like 87, because shaft is still rotating. This is another something can be implemented in this servo, which would wait before this to report the value before this thing is actually reach the position, because it knows. Now it knows. I will go quickly in my source code. There is all source code is. I'm gonna shut this down because it's annoying me as hell. All right. In my source code, there is quite a bit of details and comments explaining how stuff works. It's very crude and basic example, which illustrates the this use case, but you can build upon it. Like, this is a general idea, but because this microcontroller is relatively cheap, you can, if you instead of buying expensive smart servo, you can just add your microcontroller here, and it's pretty quick to add something like that to your servo. It can be any servo. Those two servos are actually quite different, but they are very similar inside, and many servos are quite similar inside, and adding this to that would be very simple. You can even 3D print some little case over here, which I'm actually already doing, in order to fit this particular thing inside the servo and make a little nice module together. This side can be like anything, as long as you're using 3-volt logic, because I2 bus here runs a 3-volt logic, not 5. Some buses can, depends on the whatever pull-up resistors configuration, but in this particular case, with this little guy, you have to use 3-volt logic. Another positive thing, that you would be able to reprogram your servo, because there is a USB here. You can just connect, imagine this is one unit, you can connect USB here to your computer and put any sort of whatever software you want, any sort of logic. So you can make, you can set this speed for this particular servo. You can set acceleration, deceleration. Everything would be possible inside this little microcontroller, and this little controller is more than capable of doing all this. And for example, if you have many servos, very complex thing, this will offload all this operation from this microcontroller to a bunch of these sort of controllers. Everything obviously depends on the price. If your project became too complex with bazillion of wires, probably better to offload, and if you are using only a few servers, it's no big deal. You can still use main controller and connect everything to it. This is roughly it. I hope that was useful. I still gonna finish this up and make it much nicer than just a whole bunch of wires, but I really wanted to share with you first of all the idea, and secondly that those two microcontrollers from Adafruit are really awesome for something like that. You can quickly develop your product, and especially I love this little guy because it's so tiny and so powerful. I think that's gonna be it. This is essentially a nutshell of this prototype project. I hope you guys like it. If you like more stuff like this, please sign and ring a bell. And if you have any comments, ideas, please comment them under in this video or on my website. Thank you guys for watching. See you next time. Have a nice day.